galaxy burned in the darkness, fully formed in a universe barely 300 million years old. Not a smear at the edge of detection. A structured disk of stars, impossibly bright, when nothing that size should yet exist. The James Webb Space Telescope captured it in the summer of 2022. Within months, the contradictions multiplied. Galaxies too massive for their age, black holes too large to have grown in time, an expansion rate that two independent methods refused to agree on, and on one distant world, a molecule that on Earth is produced only by living things. For decades, the standard model of cosmology told a clean, orderly story of how the universe assembled itself, and no one had the instruments to argue. Then, on Christmas Day, 2021, a $10 billion telescope launched from the coast of French Guiana and opened its golden eye 1.5 million kilometres from home. What it found in less than 3 years has forced astronomers to confront the first billion years of cosmic history, not because the universe is broken, but because its opening chapter was far stranger than anyone had written. Today, we trace the gamble, unravel the mysteries, and follow the faintest signal to the threshold of life itself. If this is your first time here, subscribe and come along for the ride. The light has already arrived. Let us show you what it holds. There is a particular kind of courage required to spend $10 billion on a machine that cannot be repaired. Not the courage of a pilot who can improvise when something fails. Not even the courage of an engineer who builds redundancies into every system. This is something quieter and more unsettling. The courage to fold the most complex observatory ever constructed into the nose cone of a rocket, launch it 1.5 million kilometres from Earth, and then watch it unfold, piece by piece, mechanism by mechanism, knowing that a single jammed hinge, a single stuck latch, a single misaligned mirror segment would turn 3 decades of work into the most expensive piece of debris ever placed in space. The James Webb Space Telescope began not as a machine, but as a question. By the mid-1990s, the Hubble Space Telescope had already transformed our picture of the cosmos. It had measured the age of the universe. It had revealed the accelerating expansion driven by dark energy. It had captured galaxies so distant that their light had been travelling for over 13 billion years. But Hubble had a fundamental limitation. It observed the universe primarily in visible and ultraviolet light, and the most ancient objects in existence, the first stars, the first galaxies, the first light to shine after the Big Bang, have had their wavelengths stretched so profoundly by the expansion of space that they have shifted entirely out of the visible spectrum and into the infrared. To see the very beginning, you needed a different kind of telescope altogether. Not one built for light the human eye can detect, but one built for warmth, for heat, for the faintest thermal whisper of objects 13 billion years away. In 1996, a committee convened at the Space Telescope Science Institute in Baltimore to answer a deceptively simple question: what comes after Hubble? They called their proposal the Next Generation Space Telescope. The initial vision was ambitious but bounded. A mirror larger than Hubble's, sensitive to infrared wavelengths, orbiting not the Earth, but a gravitational sweet spot called the second Lagrange point, 1.5 million kilometres away, where the telescope could keep its back permanently to the Sun, the Earth and the Moon, shielding itself from their heat. The projected budget was roughly $1 billion. The target launch date was 2007. According to Eric Smith, who would later serve as the program's director at NASA, the telescope required the invention of 10 entirely new technologies before it could be built. None of them existed when the project began. What followed was a quarter century of ambition outrunning every timeline, every budget, and nearly every political will to sustain it. The mirror grew to 6.5 meters in diameter, so large it could not fit inside any existing rocket fairing and would have to be folded origami-like for launch. The sun shield became a 5-layered membrane the size of a tennis court. The instruments became more sensitive, the engineering more intricate, and the cost swelled, from 1 billion to 5 billion, then toward 10. In 2002, the telescope was renamed the James Webb Space Telescope, after a former NASA administrator. By 2011, the delays had become politically unbearable. The United States House of Representatives voted to cancel the project entirely. It survived, barely, saved by scientists, advocates, and the sheer gravitational pull of the investment already sunk into its frame. By the time it was finished, the telescope had consumed more than a third of NASA's entire astrophysics budget over 2 decades. Other missions were delayed or reshaped. The Nancy Grace Roman Space Telescope, the next great priority in American astrophysics, would not launch until the late 2020s, in part because Webb had absorbed the resources that might have built it sooner. Careers rose and fell on its timeline. In 2018, with the project still hemorrhaging schedule confidence, NASA appointed Gregory Robinson as program director. Robinson was methodical, blunt, and relentlessly focused. He raised the team's schedule efficiency from 50% to 95%. His supervisor would later call him the most effective mission leader in the agency's history. It was Robinson, more than any single engineer or scientist, who carried the telescope from crisis to launch pad. And then, on Christmas morning, 2021, an Ariane 5 rocket lifted off from Kourou, French Guiana, carrying the folded observatory into the sky. Astronomers around the world watched from their homes, many holding their breath. Some had spent their entire professional lives waiting for this single moment. A generation of astronomers had proposed observations, written grants, and built instruments for a telescope that did not yet exist, betting their careers on a machine that kept slipping further into the future. The launch was nearly flawless, so precise that the telescope used far less fuel for its course corrections than planned, extending its potential operational lifetime from 10 years to 20 or more. But the launch was only the beginning. Over the next 29 days, as the observatory coasted toward its destination 1.5 million kilometres from Earth, it had to become itself. Lead Mission Systems engineer Mike Menzel had described the deployment as the most complicated sequence of events NASA had ever attempted. Every component that had been folded, stowed, and compressed for the journey now needed to open, extend, and lock into place. In sequence, in the vacuum of space, with no possibility of human repair. The sun shield deployed first. 5 gossamer layers of Captain, each thinner than a human hair, separated and pulled taut by a network of cables, pulleys, and motors. When fully extended, the shield stretched roughly the length of a tennis court, creating a thermal wall between the blazing heat of the sun and the frigid darkness the instruments demanded. The temperature difference between the two sides exceeded 300 degrees Celsius. On the hot face, the membrane baked in direct sunlight. On the cold side, the telescope began its slow descent toward the temperatures of deep space. Then the secondary mirror swung outward on the end of a slender boom, positioning itself in front of the primary. Then the 2 side wings of the primary mirror, each carrying 3 hexagonal segments of gold-coated beryllium, folded into place and locked. In total, 344 individual mechanisms had to function correctly in this sequence. Everyone was a single point of failure. Not a single one failed. The mirror is an engineering achievement that borders on the absurd. 18 hexagonal segments, each roughly 1.5 meters across, carved from beryllium, a metal chosen for its exceptional stability at cryogenic temperatures. Each segment is coated with a layer of gold barely 100 nanometers thick. Gold, because no other readily available material reflects infrared light with such efficiency. Behind each segment sit actuators capable of adjustments as small as 10 nanometers, approximately the width of a strand of human DNA. When aligned, these 18 pieces function as a single collecting surface, more than 6 times the area of Hubble's mirror, sensitive enough to detect the faintest infrared glow from the edge of the observable universe. But raw collecting power means nothing without thermal silence. An infrared telescope is, by definition, a heat detector, and that creates a paradox. The observatory must be colder than the objects it observes, or its own thermal glow will drown out the ancient signals it was built to find. The sun shield solves 1/2 of that equation, dropping temperatures on the instrument side to below minus 233 degrees Celsius. The 4 science instruments, near CAM, the primary imager, near SPEC, a multi-object spectrograph capable of observing over 100 objects simultaneously, the Canadian-built Fine Guidance Sensor and NIRIS, and the mid-infrared instrument, MIRI, each operate in this deep cold. But MIRI, built by a consortium of European institutions and designed to observe the longest infrared wavelengths, demands something colder still. It carries its own active cryocooler, chilling its detector to minus 266 degrees Celsius, 7 degrees above absolute zero. At that temperature, MIRI becomes one of the coldest manufactured objects in the solar system. It has to be. The photons it hunts are so faint, so low in energy, that even a whisper of warmth from the instrument itself would erase them entirely. For 6 months, the telescope cooled. Its mirrors were aligned through a painstaking process, overseen by telescope manager Lee Feinberg and his team at Goddard, that turned 18 separate images of a single star into one sharp, unified point of light. Each instrument was calibrated, tested, and declared ready. The commissioning team had written 207 contingency plans for the unfolding and setup sequence. Not one of them was needed. By early July of 2022, the James Webb Space Telescope had reached its orbit at L2, unfolded its shield, aligned its mirror, cooled its instruments to within a breath of absolute zero, and turned its golden eye toward the darkness. It was ready, and on the 12th of that month, the world would see what it could do. On the 12th of July, 2022, the world saw what it could do. The first images were released during a televised broadcast from NASA's Goddard Space Flight Center, and the effect was immediate. There was the deep field, a long exposure aimed at galaxy cluster SMA CS0723, a massive gravitational lens that bends and magnifies the light of objects far behind it. In a patch of sky no larger than a grain of sand held at arm's length, thousands of galaxies appeared, spirals, ellipticals, faint red smears stretched into arcs by the warping of space-time itself. Some of those galaxies had never been seen before by any instrument. Their light had been travelling for over 13 billion years, emitted when the universe was still in its infancy. stretched into the infrared by the expansion of space during every one of those billions of years. And now, finally, something could catch it. Hubble had taken its own deep field image back in 1995, pointing at a seemingly empty patch of sky for 10 consecutive days. What it found, thousands of galaxies in a void where none were expected, had reshaped our understanding of the cosmos and become one of the most important photographs in the history of science. Webb's deep field reached further and resolved more sharply, but what made it remarkable was not just depth, it was speed. An exposure that would have taken Hubble weeks to approximate at comparable depth was achieved by Webb in a matter of hours. The infrared sensitivity, the mirror's vast collecting area, the cold silence of its instruments, all of it combined into something that was not merely a more powerful telescope. It was a fundamentally different way of seeing. Alongside the deep field came 4 other images, each chosen to demonstrate a different capability. The Carina Nebula, a stellar nursery roughly 7,600 light-years away, was rendered in staggering detail. Towering cliffs of gas and dust sculpted by the radiation of young stars burning within them. Structures so fine that they looked almost geological, like canyon walls carved by an invisible river. The Southern Ring Nebula revealed concentric shells of expelled gas, glowing in colours that traced the chemical fingerprints of a dying star's final breath. Stephan's Quintet, a group of 5 galaxies locked in a gravitational embrace, showed tidal tails and shock waves in the infrared that had been invisible in earlier observations. And then there was the spectrum. Not an image, but a graph. The transmission spectrum of WASP 96b, a gas giant roughly 1100 light-years from Earth. As the planet crossed in front of its host star, Webb captured the starlight filtering through its atmosphere and measured the wavelengths that were absorbed along the way. The result was unmistakable. Water vapour, present in the atmosphere of a planet orbiting another star, resolved with a clarity that no previous telescope had achieved. It was a quiet announcement of something enormous. The era of reading alien atmospheres had begun. Klaus Pontoppidan, the telescope's project scientist, described the experience of processing the first data as surreal. The instruments were performing at or above their design specifications across every mode. Garth Illingworth, an astronomer at the University of California, Santa Cruz, who had been involved with the concept since the late 1980s, called it the culmination of a generational effort. For a community that had endured decades of delays, cost overruns, and the constant political threat of cancellation, the moment carried a weight that went beyond science. Everything, it seemed, was working better than anyone had dared to hope. But the beauty of those first images carried a quiet deception. They were chosen, in part, for their visual impact, objects that would translate well to a press conference, that would justify decades of spending to a public audience. The real science was already underway in less photogenic form, buried in spreadsheets and spectral plots and calibration files that had been flowing to research teams around the world for weeks. And inside that data, something was wrong. Not wrong with the telescope, wrong with the universe. The framework that cosmologists had spent 3 decades building, the model known as lambda cold dark matter, or lambda CDM, is one of the most thoroughly tested descriptions of reality ever constructed. It rests on a simple but powerful principle. The universe assembles itself from the bottom up. After the Big Bang, 13.8 billion years ago, the cosmos expanded and cooled. Tiny fluctuations in density, seeded during inflation, grew under the pull of gravity. Dark matter clumped first, forming invisible scaffolding. Ordinary matter, hydrogen, helium, traces of lithium, fell into those gravitational wells, cooled and collapsed into the first stars. Those stars burned fast and died violently, scattering heavier elements into their surroundings. The enriched gas condensed again into new generations of stars, and gradually, over hundreds of millions of years, small collections merged. Dwarf galaxies combining into larger galaxies into clusters, clusters into the vast filamentary web that stretches across the observable universe today. This is hierarchical assembly. Small to large, simple to complex. It is patient, gravitational and slow, and for 30 years it matched almost everything we observed. Hubble showed us distant galaxies at high redshifts, meaning we were seeing them as they existed billions of years ago, and those galaxies looked appropriately young, small, faint, chaotic, still in the process of becoming something larger. Then Webb looked deeper, and the picture shattered. Among the very first scientific results to emerge from the telescope's data were measurements from the Cosmic Evolution Early Release Science Survey, a program led by Stephen Finkelstein at the University of Texas at Austin. His team, along with dozens of others working independently, began identifying galaxies at redshifts of 11, 12, 13 and higher, distances so extreme that the light had been emitted when the universe was barely 300 million years old. At those distances, lambda CDM predicts that you should find only the faintest, most primitive collections of stars, proto-galaxies still fumbling through their earliest stages of assembly. What the telescope found instead were galaxies that appeared massive, luminous, and in some cases structurally mature. Not shapeless clumps of gas and young stars, but objects with recognizable form, including, astonishingly, stable rotating disks. Haojing Yan, an astronomer at the University of Missouri, identified 87 distant galaxy candidates behind the gravitational lens of SMACS 0723 alone, many dating to between 200 and 400 million years after the Big Bang. Even accounting for the possibility that some were closer objects misidentified by photometric methods, the sheer number was startling. The SEER survey catalogued over 850 early galaxies with measured distances and classified shapes. Jehan Kartaltep, working at the Rochester Institute of Technology, confirmed that disk structures were present among them. Galaxies that had settled into ordered rotation in an era when the cosmos should have been too violent and too young for anything of the kind. This was not universal. Lola Dan Harve at the Cambridge Kavli Institute found that the majority of early galaxies still showed turbulent, disordered kinematics, chaotic motion consistent with a universe in upheaval. But the fact that any of them had achieved structural order was itself the surprise. The implications landed hard. If these galaxies were as massive as their brightness suggested, they had converted available gas into stars at rates that no existing model could reproduce. In the local universe, the efficiency of star formation, the fraction of available gas that actually becomes stars in any given cycle, sits at roughly 1 to 2%. To explain what Webb was seeing, that number would need to be closer to 20%, possibly higher. The early universe, it seemed, had been running its stellar engines at a pace that theorists had not merely underestimated, but fundamentally failed to predict. Some researchers cautioned that apparent brightness might not tell the whole story. Tom Bax, working at Nagoya University with data from the ALMA radio array, suggested that warmer than expected dust in these early galaxies could mimic the signature of much larger dust masses, inflating apparent luminosity without requiring such extreme star formation. It was a plausible correction. But even the most generous adjustments left a surplus the models couldn't comfortably absorb. The reaction was swift and loud. Headlines declared the standard model broken. Comparisons circulated widely. Finding these galaxies was like arriving at a maternity ward and discovering fully grown teenagers. But within the research community, the response was more measured. Rachel Somerville, a galaxy formation theorist at the Flatiron Institute, framed the real question with care. The challenge was not necessarily to the cosmological model itself, the Big Bang, dark matter, dark energy, but to the astrophysics embedded within it. The rules governing how gas collapses, how stars ignite, how feedback from supernovae regulates growth, these were built on assumptions, not first principles. And assumptions, when confronted with better data, are exactly the things that break first. The question was no longer whether something unexpected had happened in the early universe. The question was how deep the revision would need to go. The answer, or at least part of it, arrived from an unexpected direction. Among the galaxies that Webb found in the early universe, a peculiar population stood out. They were compact, strikingly red, and far more numerous than any model had predicted. Astronomers began calling them little red dots, a name that stuck precisely because it was so scientifically undignified. These objects appeared in survey after survey, 10 to 100 times more abundant than expected, and they resisted easy classification. Their redness suggested extreme dust, or extreme activity, or both, but the details refused to resolve cleanly into any existing category. Catherine Chorowski, a graduate student at the University of Texas at Austin, working within the Sears collaboration, provided a crucial piece of the puzzle. Her analysis showed that many of the little red dots hosted rapidly feeding black holes at their centres. As gas spirals into a black hole, friction heats it to extraordinary temperatures, causing it to glow intensely, and that glow contaminates the light of the surrounding galaxy, making it appear far brighter and more massive than the stars alone would produce. A modest collection of young stars, viewed through the haze of a gorging black hole, can masquerade as something rivaling the Milky Way. When Chorowski and her colleagues removed these objects from their sample, the remaining early galaxies no longer appeared to violate the standard model. The cosmic crisis, it seemed, had been at least partly a case of mistaken identity. But removing the little red dots did not make the problem disappear entirely. Even without them, there were still roughly twice as many massive galaxies in the early universe as Lambda C DM predicts. Not enough to shatter the model, but enough to demand that something within it be revised. The question shifted. It was no longer whether the standard cosmological framework was broken. It was whether the astrophysics of star formation, the messy, turbulent, deeply local process by which gas becomes stars, had been understood correctly for the first billion years. The leading explanation centres on efficiency. In the nearby universe, the conversion of gas into stars is remarkably wasteful. Only about 1 to 2% of available gas in a typical galaxy form stars at any given time. The rest is blown outward by stellar winds, radiation pressure, and the shock waves of supernova explosions. But in the early cosmos, conditions were different. Gas densities were far higher. Galaxies were more compact. The gravitational pull holding that gas in place was stronger relative to the forces trying to expel it. The feedback mechanisms that slow star formation today may simply have been overwhelmed. The gas stayed put, and when gas stays put, it forms stars. Models developed by Guochao Sun and collaborators explored this possibility in detail. Their simulations showed that early galaxies could undergo rapid, intermittent bursts of star formation, surges during which the rate of new star production increased by as much as a factor of 10 over roughly 100 million years. These timescales matched the lifetimes of the most massive stars, making the behaviour physically reasonable. A galaxy caught during one of these bursts would blaze with luminosity, appearing far more massive than it would during a quieter phase. Timing, in other words, mattered as much as physics. There is another possibility, one that reaches deeper into the conditions of the primordial cosmos. The initial mass function, the distribution of masses among newly formed stars, may have been fundamentally different in the early universe. In the Milky Way and its neighbours today, the majority of stars form with masses close to that of the Sun. But theoretical work suggests that in the metal-poor, high-temperature environment of the first billion years, stars may have formed systematically larger. Massive stars are vastly more luminous than their smaller siblings. A galaxy filled with them would blaze with ultraviolet light that, after 13 billion years of cosmic expansion, arrives at precisely the infrared wavelengths Webb was built to detect. If this top-heavy initial mass function was the norm, it would explain why those distant galaxies appear so unexpectedly bright, not because they contain more stars, but because their stars are individually far more powerful. Julian Munoz at the University of Texas at Austin and Nashwan Sabti at Johns Hopkins tested whether these astrophysical explanations were sufficient, or whether something more radical, a change to the cosmological model's treatment of early universe density, was needed. Their analysis concluded that the astrophysical solutions alone could account for the data. The cosmology, it appeared, could hold. What needed rewriting was the story of how stars were born within it. The distinction matters. Headlines had declared the universe broken. The reality was more measured, but no less fascinating. The universe's opening chapter was not wrong, just far more vigorous than anyone had written. The story of the early universe grew stranger still when astronomers turned their attention from the galaxies themselves to what lay at their hearts. Supermassive black holes sit at the centres of most large galaxies, including our own, and their masses range from millions to billions of times that of the Sun. In the nearby universe, there is a well-established relationship between the mass of a supermassive black hole and the total mass of stars in its host galaxy, roughly 1 to 1,000. This ratio held so consistently across every galaxy ever measured that it became one of the anchor points of modern astrophysics. Galaxies and their central black holes, it seemed, grew together in a kind of cosmic partnership, each regulating the other over billions of years. Webb shattered that picture in the first billion years. Fabio Picucci, working at the Harvard and Smithsonian Center for Astrophysics, led a statistical analysis of 21 galaxies observed through 3 published Webb surveys, each lying between roughly 12 and 13 billion light-years away. The black holes at the centres of these galaxies were not the modest anchors the local relationship predicted. They were enormous, 10 to 100 times more massive relative to their host galaxies than the well-established nearby ratio would allow. In some cases, the black hole's mass was comparable to the combined mass of every star in the galaxy around it. The partnership, in the earliest epochs, looked nothing like a partnership at all. It looked as though the black hole had arrived first and the galaxy was still catching up. Roberto Maiolino at the University of Cambridge confirmed the pattern independently, finding overmassive black holes across a range of early Webb observations. This was not an anomaly in one dataset. It was a population 10 to 100 times more abundant than the census of mature quasars had led anyone to expect. The question this raised had haunted astrophysics for over 2 decades, long before Webb launched. How did these black holes get so large so quickly? The problem is one of basic physics. When a black hole feeds, pulling in gas and dust from its surroundings, the infalling material heats up and radiates intensely. That radiation pushes outward, opposing further infall, creating a natural speed limit for growth called the Eddington limit. Even feeding at this maximum rate without pause, a stellar mass black hole of perhaps 10 to 100 solar masses would need billions of years to reach supermassive proportions. Yet Webb was finding black holes of millions of solar masses, actively feeding less than 1 billion years after the Big Bang. The arithmetic simply did not work. One solution is that the first black holes did not start small. If, instead of forming from the collapse of individual massive stars, some early black holes formed from the direct collapses of enormous primordial gas clouds, bypassing the star stage entirely, they could have begun life at masses of tens of thousands, perhaps even 100,000 solar masses. These heavy seeds would require far less growth to reach the scales Webb was observing. Evidence for this pathway arrived when Priyamvada Natarajan at Yale University identified a candidate called UHZ1, a black hole observed through Webb that displayed signatures consistent with direct collapse, existing at a time when the universe was barely 400 million years old. If confirmed, it would represent the first observational evidence that this theoretical pathway actually occurred. But the heavy seed model is not the only possibility, and the early universe may not have required such exotic origins at all. Daxel Mehta, a doctoral researcher at Maynooth University in Ireland, working with John Regan, published simulations in Nature Astronomy, demonstrating that even ordinary stellar mass black holes, light seeds, could grow spectacularly fast under the right conditions. The key was the environment. In the turbulent, gas-rich cosmos of the first few 100 million years, dense streams of cold material could pour onto a black hole from multiple directions simultaneously, overwhelming the radiation pressure that would normally enforce the Eddington limit. The feeding was not orderly. It was chaotic, relentless, and far faster than anything possible in the more settled universe of today. Christina Eilers at the Massachusetts Institute of Technology added another layer of complexity. Her Webb observations of 5 early quasar environments revealed something unexpected. Some of the earliest supermassive black holes appeared to exist in surprisingly sparse surroundings, not in the dense galactic overdensities that merger-driven growth models would predict. If some of these black holes grew massive in relative isolation, the mechanisms of their growth become even harder to explain through conventional pathways alone. The picture that emerged was not a single clean answer, but a landscape of competing possibilities. Heavy seeds, light seeds feeding beyond their theoretical limits, chaotic accretion in turbulent gas, and environments that defied expectation, all of them potentially at work, perhaps simultaneously, in a cosmos that was younger, denser, and wilder than anyone had appreciated. The early universe, it seemed, did not merely permit the rapid growth of black holes. It demanded it. While the early universe was rewriting the rules of galaxy formation and black hole growth, the James Webb Space Telescope was simultaneously sharpening one of cosmology's most persistent and uncomfortable mysteries, a problem that predated Webb by more than a decade. The universe is expanding. This has been established since Edwin Hubble's observations in the 1920s, and the rate of that expansion is described by a single number, the Hubble constant. Measuring it precisely should be straightforward in principle. Determine how fast distant galaxies are receding from us, and how far away they are, and the ratio gives you the expansion rate. In practice, it has become one of the most contentious numbers in all of physics. The difficulty is that there are two fundamentally different ways to measure it, and they refuse to agree. The first method looks backward, using observations of the cosmic microwave background, the faint thermal radiation left over from the Big Bang, to calculate what the expansion rate should be based on the physics of the early universe. The Planck satellite, which mapped this radiation with extraordinary precision, yields a Hubble constant of approximately 67 to 68 kilometres per second per megaparsec. The second method looks forward, measuring distances to nearby galaxies using Cepheid variable stars, a type of pulsating star whose brightness is directly related to its period of oscillation, and then extending those measurements outwards using type 1a supernovae as standard candles. This approach, led for 2 decades by Nobel laureate Adam Rees and the SHOES team at Johns Hopkins University, consistently yields a value of approximately 72 to 73. A gap of 5 or 6 kilometres per second per megaparsec may sound modest, but the statistical significance of the disagreement is severe. Both measurements are extraordinarily precise, and their error bars no longer overlap. Either one of them is wrong, or both are right, and something fundamental about the universe remains unaccounted for. Before Webb, a plausible escape existed. Hubble's infrared vision, while revolutionary, was limited. When observing Cepheid variables in distant galaxies, the images often blurred together with neighbouring stars, a problem called crowding, which could systematically inflate the Cepheids' apparent brightness and skew the distance measurements. If the distances were wrong, perhaps the tension would dissolve. It was a reasonable concern, and Wendy Friedman at the University of Chicago had pressed it for years, arguing that contamination from nearby stars could account for at least part of the discrepancy. Webb eliminated that escape route. Its sharper infrared vision reduced background contamination by a factor of roughly 8 compared to Hubble, cleanly separating the Cepheids from their stellar neighbours. The SHOES team, led by Rees, with graduate student Xiang Li conducting much of the new analysis, published their results in the astrophysical journal Letters in February 2024. The Hubble constant derived from Webb's Cepheid observations came in at 72.6 kilometers per second per megaparsec, nearly identical to Hubble's own measurement of 72.8 for the same set of galaxies. The crowding was real, but it had not been the cause. The tension survived. Friedman mounted her own Webb program, observing 11 galaxies using 3 independent distance indicators: Cepheids, the brightness of the brightest red giant stars at the tip of the red giant branch, and carbon-rich asymptotic giant branch stars, known as JAGB stars. Her tip of the red giant branch and JAGB results fell lower, between 68 and 71.5, closer to the Planck value. But her own Cepheid measurements from the same data still yielded 72, landing squarely with the SHOES results. The instruments agreed, the methods did not. By December 2024, the Rees team had published their largest Webb study to date, confirming Hubble's accuracy across every calibration method, and ruling out measurement error with very high confidence. The tension was not an artifact, it was real. The implications are profound. If both measurements are correct, if the universe's expansion rate truly is different when measured from its infancy versus its present, then something is missing from the standard model. Perhaps a component of dark energy that changes over time. Perhaps an unknown particle or interaction in the early universe that altered the rate of expansion before the first galaxies formed. Perhaps something no one has yet imagined. Webb did not solve the Hubble tension. It made the question inescapable. But the telescope's reach extended far beyond cosmology. The same infrared sensitivity that revealed impossible galaxies and deepened the expansion mystery also opened an entirely different frontier. One that had nothing to do with the distant past and everything to do with the worlds orbiting other stars. For decades, the study of exoplanets had been a science of detection. Astronomers could find planets by the wobble they induced in their host star, or by the faint dip in starlight as they crossed in front of it. But they could say almost nothing about what those planets were actually like. Were their skies clear or clouded? What gases filled their atmospheres? Were the conditions remotely compatible with life as we understand it? These questions sat tantalizingly beyond reach, because answering them required something no telescope before Webb could deliver: the ability to read the chemical composition of an alien atmosphere with precision. The technique is called transmission spectroscopy, and the principle is elegant. When a planet passes in front of its star, a thin ring of its atmosphere is backlit by starlight. Different molecules absorb different wavelengths of that light. Water vapour absorbs at certain infrared frequencies, carbon dioxide at others, methane at still others. By comparing the star's spectrum with and without the planet in transit, astronomers can identify the chemical fingerprints of the atmosphere itself. Hubble had performed crude versions of this measurement for a handful of large, hot planets. Webb turned it into a precision science. The showcase was WASP-39b, a hot gas giant roughly the mass of Saturn orbiting its star at a distance of just 7 million kilometres, so close that its atmosphere bakes at over 800 degrees Celsius. It was not a promising candidate for life, but it was an ideal laboratory for atmospheric chemistry, and the results were extraordinary. 5 research teams, working with data from 3 of Webb's instruments, published their findings simultaneously. In the atmosphere of a single planet 700 light-years away, they identified water vapour, carbon dioxide, the first detection of that molecule in any exoplanet atmosphere, sodium, potassium, carbon monoxide and sulfur dioxide. The sulfur dioxide was a particular revelation. It is not a gas you would expect to find simply sitting in a hot atmosphere. Its presence requires photochemistry, chemical reactions driven by the ultraviolet radiation of the host star, breaking apart other molecules and recombining them into new compounds. This was not a static chemical inventory. It was evidence of a living, dynamic system, an atmosphere actively shaped by its star. The data also revealed something subtler. The cloud structure of WASP-39b was patchy, not uniform. The first indication that exoplanet clouds, like those on Earth, can break apart and reform, creating windows of varying opacity across the atmosphere. Adina Feinstein at the University of Chicago was among the researchers who helped identify these signatures, and Natalie Battaglia at the University of California, Santa Cruz, who had coordinated much of Webb's early exoplanet program, described the collective detection as transformative. Mercedes Lopez Morales at the Harvard and Smithsonian Center for Astrophysics noted that the richness of the spectrum exceeded what many had expected even the telescope's most optimistic projections to deliver. But if WASP-39b represented the best of what Webb could do with large, cooperative targets, the TRAPPIST-1 system delivered a colder lesson TRAPPIST-1b, a rocky planet roughly the size of Earth orbiting a cool red dwarf just 40 light-years away, had been one of the most discussed candidates for potential habitability. Webb's thermal emission observations, measuring the heat radiating directly from the planet's surface, showed that TRAPPIST-1b almost certainly lacks any significant atmosphere. The surface temperature matched what you would expect from bare rock absorbing and re-radiating starlight, with no insulating blanket of gas to redistribute the heat. For a planet that had inspired years of speculation, it was a sobering verdict. The broader picture was one of extraordinary capability meeting extraordinary difficulty. Webb could dissect the atmospheres of gas giants with unprecedented clarity, but rocky planets, the ones that matter most for questions of habitability, remained at the very edge of detection. No definitive atmosphere had been confirmed on any rocky exoplanet. The challenge is one of scale. A gas giant atmosphere extends many times the planet's radius, creating a thick ring of absorbing gas during transit. A rocky planet's atmosphere, if it exists at all, is a thin skin. Its spectral features perhaps 5 or 10 times fainter than those of a comparable gas giant. Detecting carbon dioxide in a nitrogen-rich atmosphere around an Earth-sized world requires measuring absorption across multiple atmospheric scale heights, and the signals involved are faint enough to vanish into the noise floor of even Webb's instruments. The telescope had opened the door to atmospheric characterization as a science. Walking through it for the worlds that mattered most would take time, patience, and almost certainly more observing hours than any single program could provide. What it had already proven, though, was that the door was open at all. And for one particular world, stranger than WASP-39b, more tantalizing than any planet in the TRAPPIST-1 system, what Webb found on the other side would become the most debated result in its young history. K2-18 b orbits a red dwarf star 124 light-years from Earth. It is roughly 2.6 times the radius of Earth. Too large to be rocky in the familiar sense, but too small to be a gas giant. It sits within its star's habitable zone, receiving roughly the same total starlight as our own planet, and for years before Webb launched, it had drawn attention as a candidate for a Hycean world, a planet wrapped in a thick, hydrogen-rich atmosphere with a liquid water ocean beneath. In 2023, Niku Madhusudan at the University of Cambridge pointed Webb at K2-18b and found something remarkable. The near-infrared data revealed methane and carbon dioxide at high statistical confidence, the first carbon-bearing molecules ever detected in the atmosphere of a planet orbiting within a habitable zone. The combination was striking. On a world with a hydrogen-rich atmosphere, the simultaneous presence of methane and carbon dioxide without significant amounts of ammonia is difficult to explain through geology or atmospheric chemistry alone. It was consistent with the Hycean model, a planet where an ocean might play a role in regulating what gases the atmosphere contains. But buried in the same data was something far more provocative, a faint spectral feature at a wavelength associated with dimethyl sulfide. On Earth, this molecule is produced exclusively by living organisms. Marine phytoplankton release it. Certain bacteria produce it. No known geological or atmospheric process on our planet generates it in significant quantities. If dimethyl sulfide was genuinely present in the atmosphere of K2-18b, the implications would be extraordinary. The initial detection was weak, suggestive but not conclusive. Madhusudan presented it as a hint, not a finding. But in April 2025, his team returned with new data from MIRI, Webb's mid-infrared instrument, sensitive to an entirely different wavelength range. The new analysis reported a 3 sigma signal consistent with dimethyl sulfide and possibly dimethyl disulfide. 3 sigma means roughly a 1 in 700 chance that the signal is a statistical fluke, compelling, but well short of the 5 sigma threshold that astronomy demands before a result is treated as a discovery. The reaction was immediate and divided. Madhusudan framed the result with care, emphasizing the independent wavelength range and the consistency between 2 separate instruments. Others were far less persuaded. Renyu Hu, at the Jet Propulsion Laboratory, led an independent reanalysis of the same data and found no conclusive evidence for dimethyl sulfide. Xiangmin Tsai at the University of California, Riverside, raised questions about the spectral modelling and whether the signal could be mimicked by other, less exotic molecules. NASA distanced itself publicly from any suggestion that the result constituted evidence of life. There were other grounds for caution. The concentrations implied on K218b were extraordinary, over 10 parts per million, compared to less than 1 part per billion in Earth's atmosphere. If the signal was real and biological in origin, whatever was producing it would need to be generating dimethyl sulfide at rates thousands of times greater than anything in Earth's oceans. That is not impossible. A different world could host a radically different biosphere, but it places an enormous burden of proof on the detection. And dimethyl sulfide, it turned out, is not quite the unambiguous biosignature it was once assumed to be. The European Space Agency's Rosetta mission had detected it on Comet 67 P. Churyumov-Gerasimenko, a body with no ocean, no atmosphere, and certainly no biology. The chemistry of cometary ices can produce traces of the molecule through purely abiotic processes. If it can form on a comet, there is no guarantee that its presence on a sub-Neptune necessarily points to life. The episode carried echoes of a recent cautionary tale. In 2020, a team led by Jane Greaves at Cardiff University reported phosphine in the atmosphere of Venus, another molecule considered a potential biosignature. The announcement generated global headlines. Within months, independent reanalyses challenged the detection and offered alternative explanations. The phosphine claim has never been definitively confirmed or refuted. It lingers in a scientific grey zone, a reminder that the distance between a tantalising hint and a confirmed discovery is not just a matter of better data, but of the discipline to wait for it. K218. B may follow the same path, or it may not. 16 to 24 additional hours of Webb observing time could push the signal to 5 sigma or eliminate it entirely. Sarah Seeger at the Massachusetts Institute of Technology, one of the architects of the modern biosignature framework, has noted that regardless of the outcome, what matters most is that the measurement is possible at all. A generation ago, detecting a specific molecule in the atmosphere of a planet orbiting another star was a fantasy confined to science fiction. Webb has made it routine for gas giants and tantalizingly close for smaller, stranger worlds. The question of whether we are alone in the universe has not been answered, but for the first time, it has been promoted from philosophy to observational science. The search for life on other worlds begins with a prior question, one that is easier to overlook precisely because it seems so obvious. Before you can ask whether a planet harbours biology, you need to understand how it was built. What materials went into it? What chemistry shaped its earliest moments? Whether it formed in conditions that made water possible, or carbon abundant, or atmospheres likely. Webb's infrared eye the same instrument that could read the air of a distant gas giant, was also uniquely suited to peer into the places where planets are born. Protoplanetary disks are the construction sites of solar systems. They are vast, rotating pancakes of gas and dust that surround young stars. And within them, over millions of years, grains of dust collide and stick, growing into pebbles, then boulders, then planetesimals, and eventually into the planets, moons, and asteroids that populate a mature stellar system. Before Webb, astronomers had imaged these disks in stunning detail using ALMA, the Atacama Large Millimeter/Submillimeter Array in Chile, which revealed concentric rings and gaps in the dust that hinted at young planets carving their orbits. But ALMA observed primarily the cold outer regions of these disks, the warm inner zones where rocky planets like Earth are assembled, radiated at wavelengths that required a different kind of telescope entirely. The MIND survey, the MIRI Mid-Infrared Disk Survey, dedicated over 150 hours of Webb observing time to approximately 50 protoplanetary disks, making it one of the largest coordinated programs in the telescope's early science operations. Led by Benoit Tabon at the Institute of Space Astrophysics in Paris-Saclay, the survey used Webb's mid-infrared instruments to probe the chemistry and structure of planet-forming regions at distances where terrestrial worlds take shape, within a few astronomical units of the central star. The results complicated nearly every assumption. At H.L. Tauri, a young star whose disk had already become famous through ALMA's images of sharp concentric rings, Webb revealed something the millimeter observations had missed entirely: streamers of material flowing inward from the star's outer envelope, feeding the disk from above. The disk was not a closed system, quietly assembling planets in isolation. It was being actively replenished, sustained by a flow of fresh gas and dust that could alter its chemistry and extend its lifetime in ways that static models had not anticipated. At PDS-70, a system where two young protoplanets had already been confirmed orbiting within a cleared gap in the disk, Webb's near-infrared camera captured a spiral accretion stream, material funneling from the disk onto the forming planets, and identified a candidate for a third protoplanet. Gabriele Cugno at the University of Michigan, who led the analysis, worked alongside Kevin Wagner at the University of Arizona to characterize the system's architecture. What they found was not a static snapshot, but a dynamic process caught mid-act, gas and dust spiraling inward along well-defined channels, feeding the growing worlds at measurable rates. It was the clearest view yet of how planets gain their mass, and it transformed PDS-70 from a curiosity into a living laboratory for planet formation. Other disks delivered surprises of a different kind. Shuo-10, a protoplanetary disk embedded in the extreme radiation environment of the Lobster Nebula, showed unexpectedly high levels of carbon dioxide and low levels of water in its inner planet forming zone. Standard models assume that the inner regions of most disks would be water-rich, providing the raw material for oceans on rocky worlds. Shuo-10 challenged that assumption directly, raising the possibility that some terrestrial planets may form in environments far drier than Earth's, and that the abundance of water in our own solar system may be less universal than we thought. Perhaps the most quietly significant finding concerned time. Feng Long, working at the Lunar and Planetary Laboratory at the University of Arizona, published the first detailed Webb chemical analysis of a protoplanetary disk approximately 30 million years old, far older than the typical lifespan assigned to such structures, which were thought to disperse within 10 to 15 million years. The disk was still chemically active, still processing material, still capable, at least in principle, of forming planets. If disks routinely persist longer than expected, the window for planet formation is wider than models assumed, and the diversity of planetary systems that the universe can produce grows accordingly. What emerged from the Mind survey and its companion programs was not a single revised picture of planet formation, but a richer, messier, more varied one. Disks fed by their parent stars. Disks stripped by ultraviolet radiation from massive neighbours. Disks that were wet where they should have been dry, and dry where they should have been wet. Each one a unique chemical environment, each one producing a different set of starting conditions for whatever worlds would eventually emerge. The neat, orderly story of planet formation, dust to pebbles to planets, proceeding on a predictable timeline in a predictable chemical environment, was giving way to something far more complex and far more interesting. And this, in the end, was the deeper pattern running through everything Webb had found. Not a broken universe, but a richer one. Not a crisis of cosmology, but a correction in the stories we had told about how the cosmos assembled itself during its most formative era. The galaxies that appeared too massive, the black holes that grew too fast, the expansion rate that refused to reconcile, the atmospheric chemistry of alien worlds, the construction sites where new planets take shape. Each of these discoveries, taken individually, was remarkable. Taken together, they formed something more coherent and more humbling. A portrait of a universe whose first billion years were far more active, far more efficient, and far stranger than any model had prepared us for. Star formation in the early cosmos was not the slow, wasteful process it is today. Gas converted into stars at efficiencies approaching 20%, perhaps higher in the most extreme cases, because the conditions that normally throttle it had not yet taken hold. The initial mass function may have favoured heavier stars, flooding young galaxies with luminosity that our instruments initially mistook for mass. Black holes grew to extraordinary sizes through pathways that are still being mapped. Heavy seeds collapsing directly from primordial gas. Light seeds feeding in chaotic streams that overwhelmed the Eddington limit. Or some combination of both operating simultaneously in a universe that was denser, hotter, and more turbulent than anything we see around us now. The Hubble tension survived every attempt to explain it away. Webb confirmed the accuracy of the local distance ladder with a clarity that Hubble itself could not achieve, and in doing so removed the most comfortable explanation, that the disagreement was simply a measurement error. Whatever the resolution turns out to be, it will involve new physics or a deeper understanding of dark energy, and it will come from the intersection of Webb's data with the next generation of cosmological surveys. And the question of life beyond Earth, for all the controversy surrounding K218b, moved from the realm of speculation into the realm of testable science. The molecules are there. The instruments can see them. The debate is no longer about whether we can search for biosignatures on distant worlds, but about how to interpret what we find when we do. There is something worth pausing over in that shift. For nearly all of human history, the question of whether life exists beyond Earth was a matter of belief, philosophy, or imagination. It lived alongside questions about the soul and the divine, unanswerable and therefore safe. Webb did not answer it, but by making it answerable, by placing it within reach of instruments and data and the slow, grinding machinery of scientific confirmation, the telescope changed the nature of the question itself. It is no longer a matter of what we believe. It is a matter of what we can measure. And that is a profoundly different kind of uncertainty to sit with. Joseph Silk, who holds positions at both Johns Hopkins University and the Sorbonne, has described Webb's impact as the most significant single advance in observational cosmology since the discovery of the cosmic microwave background. Michael Boylan Colchin at the University of Texas at Austin, whose early calculations helped quantify the tension between Webb's galaxy observations and the Standard Model, has been measured in his assessment. The case for purely astrophysical explanations is strong, he argues, but not yet airtight. The door to more fundamental revisions remains open. What none of these discoveries did is break the Big Bang. They did not overturn lambda CDM wholesale. They did not prove that life exists elsewhere. What they did was something more honest and ultimately more valuable. They revealed that the opening chapter of the universe's history was written in a language we had only begun to learn, and that the story we had been telling, while not wrong in its broad strokes, had been missing most of its detail. The universe was not simple in its youth. It was prolific, impatient, and astonishingly creative. And we are only now developing the vocabulary to describe what it did. The James Webb Space Telescope was built to last 5 years. Every component, the sun shield, the cryocooler, the reaction wheels that keep it pointed with sub-arc second precision, was designed to survive at least that long 1.5 million kilometres from any possibility of repair. But the Ariane 5 launch on Christmas morning 2021 was so precise that the telescope used far less propellant than budgeted for its course corrections. The fuel that remains is enough to keep Webb operational for 20 years, perhaps longer. That changes the calculus of everything the telescope has already begun. The early galaxy surveys that revealed impossible brightness were conducted with relatively shallow exposures. Deeper observations, accumulating photons over hundreds of hours, will push the frontier beyond redshift 14 into a period when the universe was barely 250 million years old. If galaxies exist even there, structured, luminous, defying the same models, it will tighten the constraints on early star formation to a degree that current explanations may struggle to accommodate. If they do not, the boundary itself will tell us something profound about when the first light in the cosmos ignited. The TRAPPIST-1 system will be observed again and again. The null result for TRAPPIST-1b was sobering but not final. The system contains 7 rocky worlds, and the outer planets, TRAPPIST-1e, F, and G, orbit within or near the habitable zone. Each will require multiple transits, observed across different wavelength ranges, to confirm or rule out a thin atmosphere. It is painstaking work, measured in years, but the stakes are difficult to overstate. A confirmed atmosphere on a rocky, temperate world orbiting another star would be among the most significant detections in the history of astronomy. K2-18b, 2, will return to Webb's schedule. The dimethyl sulfide signal sits at 3 sigma, tantalizing, unresolved, impossible to ignore. An additional 16 to 24 hours of MIRI observation could push it to 5 sigma or collapse it into noise. A confirmed detection would not prove life, but it would demand an explanation that no current model of atmospheric chemistry can comfortably provide. A null result would sharpen the boundaries of what biosignature science can realistically achieve at this distance, and redirect the search toward better suited targets. Beyond Webb, a new generation of observatories is already taking shape. The extremely large telescope, under construction in the Chilean Atacama by the European Southern Observatory, will carry a mirror 39 meters across, large enough to directly image exoplanets and measure their atmospheric composition from the ground. The giant Magellan telescope, rising on a neighbouring peak, will combine 7 mirrors into an instrument with resolving power 10 times sharper than Hubble. The Vera Rubin Observatory will catalogue billions of objects and track changes across the cosmos on timescales of days. And further ahead, the Habitable Worlds Observatory, a NASA flagship proposed for the 2040s, is being designed to do what no telescope has yet accomplished: directly image Earth-like planets orbiting Sun-like stars and search their atmospheres for signs of life. Every one of these instruments will build on the questions that Webb has opened. None of them would ask those questions in quite the same way without what Webb found first. There is a particular quality to the light that the James Webb Space Telescope collects. It is old. Some of it has been travelling since before the Earth existed, since before the Sun ignited, since before the Milky Way had finished assembling itself from the merger of smaller galaxies. By the time it reaches the gold-coated mirrors at the second Lagrange point, it has crossed distances that the human mind cannot meaningfully hold. And yet it arrives. Faint, ancient, and carrying within it the story of everything that happened at the beginning. The telescope that took 3 decades to build has, in just 3 years of operation, rewritten more of our cosmic story than any single instrument in history. It has shown us a universe that was not patient in its youth, a universe that built its galaxies too quickly, grew its black holes too large, and may have stirred the chemistry of life on worlds we are only now learning to see. The answers it has delivered are provisional. The questions it has opened may take a generation to resolve, but the light keeps arriving night after night, and the mirror keeps collecting it, and the story keeps changing. It is not finished. It has barely begun.